So today's lecture really changes tone from what we've been doing all semester long, because we're really going to start looking at the history of the Earth, almost like pages in a book. And this next figure I'm really kind of fond of. It takes Earth's history and puts it on a 12-hour clock, which I think is fun. And you can see that they make it a 24-hour clock just so you can see, like, in a day what you would expect if we were to compress all of Earth's history into 24 hours. So we're starting today with our discussion of the Hadean Eon. The Hadean Eon lasts about 13% of all of Earth history, and then we're going to follow that up and finish this chapter with the Archean Eon, which is about 32% of Earth's history. By the end of the semester, we will have finished our 24-hour clock. So let's get started. We're going to start with the Hadean Eon, of course, which is the very earliest formation of the Earth. And we learned in a previous chapter that that begins with the accretion of Earth from our solar nebula. So if you recall, the solar nebula hypothesis is the origin of the solar system, where the sun and the planets of our solar system were created from a gas cloud that was then hit by energy from a supernova, began to collapse into a disk-like structure, and under its own gravity, segregated into the outer planets, the sun, and then the inner planets. So let's pick up from that spot. All right, so here's an artist or rendition of early Earth. As you can see, it was not particularly nice. And in fact, this is a little bit further along than things actually probably looked in the Hadean Eon. Initially, Earth was homogeneous and molten. Homogeneous means pretty much the same throughout. And this is an artist's idea of what the earliest crust started to look like. But initially, Earth was incredibly hot, and there were three reasons why. One is that you have the heat of compaction, the pressure of all the material kind of condensing under its own gravity towards the center of the Earth. The second is the presence of lots of radioactive isotopes. So there's currently about half as much uranium in the core of the planet as there was during its earliest formation. So there were a lot more radioactive isotopes, and a lot of them were decaying and releasing heat during radioactive decay. And the third source of heat is the heat of accretion, that heat of how temperature goes up when pressure goes up, and pressure was going up because of what you see in this image, which is lots of impacts from extraterrestrial objects. So we call this time period the heavy bombardment period. There is lots of meteorite and planetesimals bombarding into the Earth during the earliest portion of Earth, and it's likely that it began to cool and became remelted multiple times. Another event that happened early in the Hadean Eon was the formation of the Moon, our closest cosmic body, which the current hypothesis is that the Moon was created by the impact of a Mars-sized object that astronomers have named Theia about 4.53 billion years ago. So again, the Earth was first formed about 4.56 billion years ago to our best estimate. So this is very shortly after the initial formation of the Moon, or of the Earth, sorry. And you're going to watch a video about the different competing hypotheses about the formation of the Moon, but the evidence for the formation of the Moon by the giant impact theory is there's 4 lines of it, and the first of which is that the Earth spin and the Moon spin are in the same direction. So the idea is that Theia hit Earth, that Theia vaporized, that part of the Earth's, if there was any crust at that point, that would have vaporized along with portions of the mantle. And that's represented in the fact that the composition of the Moon is similar to the composition of the Earth's mantle as well. Finally, this is consistent with observations of astronomical impacts that astronomers have observed, especially on Jupiter, where we've seen impact and we've seen vaporization, and then that material that is then ejected from a planet begins to coalesce and collapse and form these bodies that then orbit that planet. So you're going to learn again more about this in the video. There are a few important features of the moon, and there are a few important things that are missing. So the moon has no atmosphere, and it doesn't have an atmosphere for a couple reasons, but it also has, because it has no atmosphere, it has no oxygen in the area around the moon, so there's no oxygen to react with any iron-rich minerals. So a lot of the rocks that we'll see on the moon do have iron in them, but there's no iron oxide, which is typically when rocks become stained red because of the presence of hematite or other iron-rich minerals that have oxygen within them. So part of the reason that the moon has no atmosphere is because it's so small that its core is cooled and it has no plate tectonics. If you recall, the plate tectonics basically moves because there is convection within the Earth's mantle. So if there's no convection in the Earth's mantle, then there's going to be no volcanoes emitting any sort of gases to the atmosphere. And also because the core of the moon is completely cooled, there's no magnetic field. Regardless of the fact that there's a lot of iron on the moon, that iron is cooled and not sort of undergoing its own convection in the core of the Earth. So because there's no magnetic field, there's no way to block the rays of this like solar winds which the Earth has, that helps to protect the Earth's atmosphere, that thin envelope of gases that surround our planet. What we do see on the moon, however, when we look at these pictures, we see this white region, this white rock, which is referred to as the lunar highlands. They're the oldest rocks on the Earth. It's about 4.5 billion years old, rocks that are called anorthosite, which are very rich in calcium-rich feldspars. So anorthosite is actually also common. If you've ever been up to the Adirondacks in New York State and you go to the High Peaks region, a lot of the rocks in that region are anorthosites. The black regions of the moon are called lunar mare, and they are the younger rocks on the moon. They are the result of 3.5 billion year old basaltic lava flows. So when the moon was still molten, there were large impacts, and molten material from below, induced melting because of the impacts, resulted in basalt flowing up through some of those impacts. So you can see in some of these larger craters, there are these very large lava flows. So they're called lunar mare because early astronomers thought that they were like seas, and mare is a word that means sea. And it wasn't. They were just, I guess they were flood basalts. They were basalts that came up and filled in a lot of the early craters of the moon. Craters are also visible on the moon, and so that's our third feature, and we can see these. An initial understanding of the formation of the moon came largely from aerial photographs, including looking at some of those craters to figure out which crater formed first, and did all the large ones form first, and did they get progressively smaller, as you might think, because there's less cosmic debris kind of shooting around our solar system, or what? And finally, lunar breccia is just broken up chunks of rock on the moon as the result of cratering. So lots of really angular particles. Of course, there's no weathering on the moon, really, because there's no water besides in icy portions of it. And the water isn't like, it's dispersed evenly kind of throughout rocks, so it's not really present in any sort of liquid form at all. So it's just broken up chunks of rock as the result of impacts. So there's a couple cool things, though. There's actually many cool things to be learned about the impacts of the moon on the Earth. One significant impact of the moon on the Earth is called tidal friction. So tidal friction is what creates the tides on Earth, and it's the result of the gravitational attraction of the moon. So the moon is actually about 1/4 of the size of the Earth, which is very large for moons and planets. And what it does is the water in Earth's oceans is gravitationally attracted towards the moon. And so on the side of the Earth that is closest to the moon, there will be a bulge in sea level, and that's called the tidal bulge. And then while there's a tidal bulge, the Earth is rotating beneath that tidal bulge, and that water continues to move along with the rotation of the Earth. But when the water gets to this area, oops, just kidding, when the water gets to this area, inertia means it still kind of wants to go straight, but it can't, and so that water will build up on the opposite side of the Earth, and that is called the centripetal bulge. All right, so you should probably make this sketch in your notes. It feels like an important one, so I'm gonna write in. This is we call this one, oh, this word is so long, why? This is the gravitational bulge. Oh, this is perfect. I gotta figure something out here. That's gravitational bulge. And then the one on the opposite side of the Earth is called the centripetal bulge. Why are these words so long? Centripetal bulge. Okay, so you might notice that these bulges are a little bit offset from the moon, and that's because the Earth is rotating in this direction, and so it's actually bringing the bulges with it just a touch. Let's see, something I got out of this. So tidal friction is what, and I'm going to show you a little animation of this in just a second. So the tide, it creates the tides in coastal regions. So as continents rotate beneath the tidal bulges, if you're sort of, and you'll see this in the animation, as you rotate underneath the tidal bulge, your location is under high tide, and when you when you're free of the gravitational bulge here, then you're in low tide, and the Earth keeps rotating, and you go into another period of high tide when you're beneath the centripetal bulge, and back to low tide when you are not. So this friction actually, the friction that we're talking about here is that as Earth is rotating, there's actually friction between the gravitational pull of the moon. The moon actually slows the Earth down just a touch, and it releases heat. But before we get to that, let's go to this fun little animation. Oh, but I already signed up. I logged in just a second. Oh, you keep writing. Okay, I got it all worked out. All right, so here is a simulation of this. So the sun also plays a role in this as well. The sun has a gravitational pull on water on Earth as well. However, the sun is 98 million miles away. The moon is only about 230,000 miles away. So the moon ends up having a much more significant influence on the tides than the sun. The sun doesn't have none, but it's much less than the moon. So sometimes the sun, the Earth, and the moon system are all aligned like you see here. And that is what's called spring tide. And it's because the tides kind of spring forth from the Earth, and you have a big difference. And of course, this is very much exaggerated here. But you have a big difference between high tide and low tide. I'm going to put the speed at about there and start to play this. So here is a person, and they are fishing during high tide. And as we start, oh, that's too fast. Wait, oh, I made it faster. Okay, this is fantastic. So in a given day, this guy's in high tide, and now he's in low tide, back to high tide. So what I want you to notice, I'm going to pause this for a second. I was going faster than I was ready for. So these gravitational bulges primarily stay in line with the moon, right? So we still have the gravitational bulge here, the centripetal bulge here, and you can see here there's a slightly smaller difference between high tide and low tide, right? You can see that the bulge here is a little bit, the ocean sea level here is a little bit higher, and that's because now the sun and the moon are not both pulling water in the same direction, because the moon is pulling it in this direction, but the sun is also pulling it in this direction. So and you have your lowest tidal range when, all right, now I got to speed it up just a touch, when the sun and the moon are actually at like 90 degrees from each other. So if I stop it here, where the sun is pulling in this direction. A gravitational pull of the sun is pulling water in this direction, and the moon is pulling it in this direction. What you see is there's way more water built up in the low tide region, right? So this is called neap tide. Neap tide is when the sun and the moon are pulling in opposing directions. So spring tide is when the sun and the moon and the earth are all pulling, the sun and the moon are both pulling in the same direction. Neap tide is when they're pulling in opposite directions. So as we speed this up a little bit, you're going to see that when the sun is pulling this direction and the moon is pulling this direction, we're going to go back into another spring tide. Slowly. Okay, so now the sun is pulling to the left with its gravitational pull. The moon is also pulling to the left with its gravitational pull. And you see you have the largest high tides here. And again, there's almost no water at the low tide region. So this is another period of spring tide. So it's spring tide here, right? And then it's also spring tide where we started, which was here. And that's because the moon and the sun are both pulling in this general direction. So if there's a neap tide here, similarly, there's going to be a neap tide right here. So as the moon rotates around the sun, you can see that tidal bulge, those tidal bulges rotate right along with the moon. And when it gets to about a 90-degree angle again, we have once again reached neap tide. And that's again because the moon is pulling in this direction, the sun is pulling in that direction. And we'll go back to spring tide when our moon gets to be pulling in the same general direction as the sun on the water. All right, you're gonna have a short activity to practice some of that in just a little bit. So a couple cool things that we're going to talk about before you get to practice that, though. So this friction from the gravitational attraction of the moon actually slowing down the Earth's rotation is something that we can measure. It's really cool. So these are some coral that grew during the Devonian period about 350 million years ago. And these coral every single day would secrete one little layer of growth. And that's how they sort of built up in this general direction. And so based on the thicknesses of the coral layers, you can figure out whether it was a warm season or a cooler season, like summer or winter. And that's because the corals grew faster in the summer and slower in the winter. So, and when you look at them under a microscope, you can actually see each little layer that was secreted every day by these coral. And so by counting those layers, geologists actually figured out that the day on the Earth used to be less than 24 hours, and that the Earth actually used to make, right now it rotates 365 times, right, as Earth goes one rotation around the sun. But during the Devonian period, there was a shorter time period for this tidal friction to occur. There were actually 400 days in a year during the Devonian period based on the number of little layers that you could see in Devonian coral. Okay, so this is a super cool website. It's from the Howard Hughes Medical Institute, but it's called Earth Viewer. And I'm going to acclimate you to it real quick, and then I'll show you some of the things that you can do with it. You'll have an assignment using this website later this semester because it's so fun. So you can see that this is the Earth today. 0 million years ago, there is a 392 parts per million of carbon dioxide in the atmosphere. The oxygen content of the atmosphere is 21%. The length of the day is 24 hours, and you can kind of rotate the globe around. It's really fun. But here's the really cool part, and you'll get a chance to play with a lot of these things. As we take this and drag it back, let's go back to the Devonian period, 400 million years ago. So you can see there was a little bit more oxygen. You can see that carbon dioxide was way higher 400 million years ago, but over here, you can see the length of the day was only 22 hours long. And then over here, one of the most fun parts of this is that you can rotate this globe around and see look at this, is what New York looked like 400 million years ago. So this light blue color here indicates that it was covered with a shallow sea. But what's the coolest part of this, right, is that you can see that New York was basically right near the South Pole 400 million years ago. And in fact, there was a ton of land by the South Pole 400 million years ago. So you can see India and South America, and over here is Australia. Anyway, Earth Viewer is such a fun website, and it also, there's an app for it as well. If you're working on an iPad, you'll have some fun times playing with this, because there is Ice Age Earth, where you can go and see what the Earth looked like during the last glacial maximum about 20,000 years ago. There is Warming Earth, where you can look at modern trends of climate change, which is fun. Anyway, but I wanted to really just kind of show you that 400 million years ago, that the day was shorter, and so that because the Earth is spinning faster, the distance around the sun that the Earth travels is still the same. So it ended up with there being more days in a given year, which is pretty fun. Okay, there are other factors that influence the size of some of these tidal bulges, and those are featured on this slide. So part of your activity is going to be looking at tidal friction, but then also you'll be applying some of these terms as well. So here is a diagram of the Earth's rotation around the sun. And you can see that the Earth is not always the same distance from the sun. That there are times when there is time called perihelion, where, and this is spelled wrong. There should be an I here. All right, here we go, pen. So it should be perihelion. And perihelion is when the Earth is closest to the sun in any given part of the year. Aphelion is when the Earth is farthest from the sun. And then similarly, it takes about 1 month, about 27 and a half days, for the moon to rotate around the Earth. And so there are time periods when the moon is actually a little bit closer to the Earth in a given month, and that's called perigee. And when when the moon is farthest from the Earth during any given month, that's called apogee. And so, as you might imagine, since the sun and the moon have a gravitational influence on tides, then your high tides will be higher during perigee, and your high tides will be lower during apogee because there's less pull. And similarly, in perihelion, the sun will exert a greater gravitational pull on the oceans than it will during aphelion. So these are just different astronomical changes in orbit that have an influence on the tides. So other things that the moon does to the Earth is it stabilizes the Earth's tilt quite a bit. So this is something that you learned about in physical geology, and this is called, there has to be a way for me to just like write on these things, is called obliquity. Obliquity is the sciencey word for the tilt of the Earth. Obliquity. Good. Okay, so obliquity on the Earth is one of the 3 Milankovitch cycles, which are cycles that control really whether or not the Earth is going through an ice age or not. So the Earth tilt doesn't change a whole lot. Right now it's 23.5 degrees. It can be as little as 22.5 degrees or as much as 24.5 degrees. And the reason that is so constant is because the moon, because it's fairly large, exerts a pretty reasonably good gravitational stabilizing force on the Earth. Mars, for example, has no moon. And Mars, the obliquity varies tremendously. So Mars, the obliquity or the tilt of Mars can vary from 10 degrees to 40 degrees, which would have huge variations in climate. So the stabilization of Earth's tilt helps to stabilize Earth's climate as well, which makes life on Earth just tremendously more predictable. It also means that the Earth is so heavily influenced by the moon that it is largely unaffected by the gravitational pulls of other planets. The only planet that Earth is even marginally affected by is the gravitational attraction from Jupiter, and that only occurs on either 100 or 400,000 year cycles, depending on the proximity of Jupiter. So the moon has a tremendous influence in stabilizing Earth. And so as a result, life on Earth has developed adaptations that take advantage of the constancy of the moon. One of those is night vision. This is just a creepy night vision picture that I pulled from a website. But there are organisms, right, that have developed the ability to see pretty well at night because it is an evolutionary adaptation for them to hunt at night. And so using the light of the moon, and sometimes using very little light from the moon, organisms have developed time periods where they have a hunting advantage over others. There are other organisms that have adapted to live in between high tide and low tide where very few organisms can live. And so that again gives them a biological advantage of not being eaten near as often. So intertidal organisms are organisms that are sometimes living underwater during high tide and sometimes living above water during low tide. And that includes things like clams and sea stars and barnacles, mussels, limpets. And so those organisms, if your main predator is in seawater, then presumably for many hours of the day, your main predator cannot get to you. And if your main predator is on land, then similarly, several hours of the day, the predator can't get to you because you're underwater. So these adaptations have been developed by organisms for survival, right? They are adaptations that give them an edge at survival and passing those genes on to their offspring. All right, so without further ado, let's have that fun time working a little bit more on tidal friction, and then we will come back and talk more about early Earth.